everyone and welcome to TL Eliminators CP-31 Sheet Solutions. This is Vibhaas Srivastava and today we'll be solving the 1600 rated CP-31 sheet problems, and we will start with the problem partitioning the array. Okay, so let's go to the CP-31 sheet and let's navigate to this problem, partitioning the array. Yes. Now let's just go through the problem, read it, understand it, and then we'll get right into the solution. All right. So the problem states Alan has an array a1, a2, an consisting of integers, right? So a1 till an. For every positive integer k that is a divisor of n, Alan does the following. He partitions the array into n by k disjoint subarrays of length k. In other words, he partitions the array into the following subarrays: a1 to ak, then ak plus 1 till ak a to the 2k, right? And so on. So basically k is a divisor of n, and for every k which is divisor of n, he partitions the array into this blocks of size k. Okay, Alan earns 1 point if there exists some positive integer m greater than or equal to 2, such that if he replaces every element in the array with its remainder when it's divided by m with its remainder when it's divided by m, then all the subarrays will be identical. Okay, we'll explore what this means by taking an example. Now the question says help Alan find the number of points he will earn. Okay, let us read the constraints. N goes up to 2 times 10 to the power 5 and a of I goes up to n. So also it's guaranteed that the sum of n over all test cases does not exceed 2 times 10 to the power 5, right? What do we need to output? An integer, the number of points Alan will earn. Since n is regular constraints, that is 2 times 10 to the power 5, we can easily write that the solution form, the solution would be roughly about big of n log n, right? Stuff like this, big of n log n plus maybe some constant, something like that, roughly about this much. Okay, so this is the expected time complexity. Okay, this is the expected time complexity, which we should always check before starting a question. So now let's have a look at an example and see what exactly the question is asking us. Okay, let's have a look at an example, and let's take an example with, let's say, a good amount of numbers. So let's take the fourth example, 131131. Okay, so the array is, our array A is 131131. Okay, this is the array. N equals 6. So now what are the possible divisors of 6? Divisors of 6, and that is 1 is a divisor of 6, 2 is a divisor of 6, 3 is a divisor of 6, as well as 6 is a divisor of 6. Okay, so 4 possible divisors we get. Let us make chunks of size 1, of size 2, of size 3, size 6, right? So what are the chunks we can get? We can get, first, if we make chunks of size 1, simply all the elements are separate from each other and we get an array which looks like this, right? Now, does there exist some m such that if we mod all these elements with m, these arrays become equal? Well, that exists. Let us just choose m equals 2. Then on modding, what happens? We get 1. Here also we get 1. Here also we get 1, 1, 1, and 1. And as you can see, all these arrays, these smaller partitions which we have made, are equal. So we add a point. Okay, so points becomes plus 1. All right. So at m equals 2, this divisor 1, k equals 1 is satisfied. Okay, so this is try k equals 1, and we can see k equals 1 is satisfied. Now what about k equals 3? Okay, sorry, what about k equals 2? In the case where k equals 2, again we can divide it into blocks of size 2. So we get 1 3, then we get again, then we get 1 1, then we get 3 1, right? Again, if we use m equals 2, again if we use m equals 2, we can see that this entire equation gets satisfied, and we get 1 1 1 1 1 1, right? And so on and so forth. You can check for each divisor if there exists some value m such that it makes all the arrays equal, right? Arrays equal means it needs to, for example, in the case where we have let's say 4 and 7, right? If we have, let's say or maybe 4 and 9, then we have, let's say 7 and 12. Okay, 7 and 12. Now if we want to, if these were the two blocks, let's say k equals 2, n equals 4, and we received this case, okay, then if these were the two blocks, we can choose m equals 3, and we can make that, we can make all the arrays, we can make both the arrays equal, right? You can see the first position is 1, here also the first position is 1, second position 0, second position 0. So that's what it means to make the arrays equal. You just need to make sure that each element is equal in these blocks, not just not just all the elements, right? Okay. Also, we need to make sure that this integer m is greater than or equal to 2, because obviously if we choose m equals 1, all the values will become 0, and that would be a trivial case, right? That would be too trivial. So that's why we need to ensure that there's some m greater than or equal to 2. Okay. Now, how do we approach this problem? You should already be getting some ideas that this problem is going to use some number theory ideas, maybe some GCD ideas, because it involves divisors, right? So, and modulo. So let's have a look at it. Okay. Observation 1. Okay, observation 1. And in this, let us assume that we have two blocks. So let's say the blocks are, let's say A1, A2, A3, A4, and the second block is A5, A6, A7, A8. Okay, and we're going to make some observations regarding this, which will help us solve the problem. Okay, so if we choose A1 and A5, we know that these elements must be equal, right? We know that these elements must be equal. Similarly, A2 and A6 must be equal, right? A3 and A7 must be equal, and so on, when doing modulo m, right? When doing modulo m. So under modulo m, A1 should be congruent to A5. Similarly, A2 should be congruent to A6 under the modulo of m. Okay, so how do we ensure this to be true? We can write this as an equation. Equation form, and we can write A1 mod m is equal to A5 mod m. Okay, so equation form, we can write this as A1 mod m is equal to A5 mod m. Now, does this give us some information? Yes, this gives us some information, because, for example, let's say m was 10. Okay, m was 10. Then the two numbers must have a difference which is also mod m. What do I mean by that? That means that, let's say if A1 was 12 and A2 was 32, then it is a valid condition satisfying this. As you can see, mod 10, they're equal to 2, right? But it can't be possible that A1 was 12 and A2 was 33, which would be wrong, right? That won't satisfy the above condition where m equals 10. So basically the idea is we need to check the difference. Why do we need to check the difference? Because the difference between A1 and A2, between A1 and A5 in this case, will be 0 modulo m. Why? Because whatever extra value we added onto the smaller number to reach the larger number, that value must be divisible by m, right? That must be divisible by m. That's why the remainder has not changed, right? That's why the remainder has not changed. So keep this in mind, that the absolute value of I minus ai minus a5 in this example is mod m is 0. Similarly, we can also state that the absolute value of a2 minus a6, absolute value of a2 minus a6 mod m. Why are we taking absolute value? Because we are considering the positive difference, right? We want to go from the smaller to larger. If this is also 0 and so on, for all a of, let's say, n minus k by a of n, percent m equals 0. Okay, so these conditions need to be met by some m greater than or equal to 2. Right, these conditions need to be met by some m greater than or equal to 2. Okay, let us write down our observation neatly. Observation 1, and the observation simply states that ai minus k absolute value mod m is equal to 0 for some m greater than equal to 2. If this is true, if, then we add a point. Okay, then we add a point. All right, now how do we find this particular value of m? Right, how do we find this particular value of m? Well, it's basically like we have a bunch of these equations, like a1 minus a5 mod m equals 0, a2 minus a6 mod m equals 0. So basically all we need to do is we need to choose a value which satisfies all of the following mod m to give 0. Okay, so we need to choose a value of m which satisfies all of these following equations. So basically we need to satisfy observation 2, we need to satisfy equations which look like this. Okay, so I'm just gonna call a1 minus a5 as, like, let's say x1, similarly a2 minus a6 as x2, and so on. So our equations become x1 mod m is 0, x2 mod m is 0, x3 mod m is 0, right, and so on. Xn mod n is 0. Okay, now interesting thing to observe about this equation, it means that m divides x1, right? It also means that m divides x2, right? And m divides x3, right? And so on till m divides xn, right? So bringing it back to the context of our question, what we can see is, under our question, it simply means that we can choose m, we need to choose an m, we need to see if an m exists, if an m greater than 2 exists, such that m divides abs of, let's say, ak minus a1, and then we can say abs of, okay, this will be ak plus 1 minus a1, abs of ak plus 2 minus a2, abs of ak plus 3 minus a3, and so on, right? It must divide all these differences. So this approach of using difference over here, it's a very essential idea. Okay, that absolute value of a1 minus a2 or a1 minus a5 or a1 minus ak percentage m is 0. That is only the way that these two modulus can become equal. This is a very common idea, and it's something which you should note and keep in mind. Okay, you might even see it later on in the very same CP sheet, or you might have already seen this before. Okay, and it comes often in many problems. It comes handy very often. Okay, all right, so we need to see if such an m exists, and since we want an m greater than 2, right, greater than or equal to 2, what if we try to find the largest value of m? Okay, so if the largest value of m is less than 2, we know that there is no m satisfying. Otherwise, we find an m greater than or equal to 2, so we know that there is some m satisfying, and we can add a point. Okay, we can add a point. So how do we find this largest n? Well, we simply need a number m that divides a bunch of numbers, right? We need a number m which divides a bunch of numbers. So we can say that m equals the GCD, right? GCD means greatest common divisor. So for all these numbers, whatever divisor we have, we're going to take the greatest one, right? And we're going to check if that's greater than or equal to 2 or not. So we simply need GCD of abs ak plus 1 minus a1, abs ak plus 2 minus a2, right? And so on. and so on until we have abs of an minus k, right? So until this point, we take all the GCDs, we take GCD of all these elements of these differences, and that is our value of m. If m is greater than or equal to 2, right? If m is greater than or equal to 2, in that case, we may write basically the number of points we have achieved will get increased by 1. Okay, so the number of points we have increased will get increased by 1. Now this is our second observation, or this is the like basically our solution itself. Now the final note, number of values of k, right? Number of values of k is equal to the number of divisors of n. Okay, is equal to number of divisors of n. So it will be small, right? It will be small. We know that number of divisors cannot be very large, so it will be small. Okay, the number of divisors is roughly approximated by the cube root of n. Okay, so it's a rough approximation, but it works in practice that the number of divisors of a number n is roughly cube root of n. Okay. Also, to find these divisors, you can obviously use complicated methods like sieve, but we can simply use a simple root n method as well to find it. Okay, so now we can find each possible value of k. For each possible value of k, we find the maximum value of m, which is by GCD of these differences. If m is greater than or equal to 2, we can increase the number of points we have received. Okay, we can increase the answer. So that is the final solution. Let me just write down a pseudocode for our final solution. Okay, if any of the steps were confusing, do rewind the video and reread the logic behind them. The questions, if you're new to number theory, they might be not that easy, so don't feel shy about rewinding and watching it again. I do recommend following with examples. Like, I'm giving a theoretical idea, but it's best if you follow with some examples on pen and paper if you're not able to understand some particular step. Okay, let us write the final solution. So our final solution is simply for every k that is a divisor of n, that is, initially we'll initialize answer equals 0. Okay, so for every k that is a divisor of n, initially we can set m equals 0 because we want to find the GCD of all these numbers, so we can set m equals 0. Then for, let's say, I goes from k, I goes till n, and we can increment I, right? And we can say m is the GCD of m, and so GCD is the like associative operator, so we can just do like GCD of m repeatedly, and we get the same answer as the GCD of everything, right? So that's why we're doing it. So we get m equals GCD of m, as well as this new value which we found, the absolute difference of ai minus k. Okay, this will give us the maximum value of m that is possible if m is greater than or equal to 2 or m is equal to 0, right? The number of points increases. Why do we have an additional case for m equals to 0? Well, that is simply if k covers the whole array, right? If k equals n, for that case, to handle that case only, we need m equals 0 case. All right, otherwise the GCD will obviously change from 0, right? All right, and then simply once this whole loop is done, we can print the number of points earned. Okay, we can print points earned. All right, now let's have a look at the code for this solution, and as well we'll discuss the time complexity. Okay, so here's a rough code for this, pretty much the exact same idea. I define an integer n and I take in n numbers in this vector. The function divisors generates divisors of a given number. The way I'm doing it here is a simple square root of n check. So up to square root of n, we will check which numbers are divisors. We can show that we need to check at most square root of n because either I is a divisor and then n minus I will also be a divisor, and there'll not be any other divisors, right? So it's a simple check for divisors. You can read this code. It returns a vector of divisors. Okay, Now I have got my vector of divisors of n, and my answer is 0. So this is the number of points I've earned so far is 0. For every k which is a divisor, I find my max GCD, which I name m, and I set that to 0. Okay. Now I go through each element and I take GCD of that with the difference between a of I and a of I minus k. Why this difference? Again, as I said, it's because simply a of I minus a of I minus k divided by m should equal 0, and that's why we're doing this. All right. Now, if m is not equal to 1, answer increases. Why did I write it this way? As you can see, the logic is the exact same. If m is greater than equal to 2 or m is equal to 0, that simply means m is not equal to 1, right? So if m is not equal to 1, we get more points, so I increase my answer. Finally, I output my answer. All right, so that's how we write this solution to this problem. Okay, now what is the time complexity analysis for it? I hope the solution was understandable. Let us discuss the time complexity analysis. Usually for number theory type problems, the time complexity analysis gets weird because you may do it many ways. You may do it either with this brute force approach with normal square root divisors. You can use Euclid's algorithm. You can use basically, like, you can use sieve, right? You can use the sieve of Eratosthenes to like pre-process prime, so then we can find divisors faster, right? So there are many ways to implement it, but almost any way will pass under the given time under the given time constraints. Okay, let us see. The n sums over all test cases, so we don't need to care about the number of test cases. We just need to care about n, right? So big O of n to read the input. Then to find the divisors is big O of root n, correct? The divisors function works in root n time. Okay. Now for each divisor, how many divisors there are? Again, I said a rough estimate for the number of divisors is a cube root of n. Okay, so rough estimate for the number of divisors is cube root of n. So we have this. Now what are we doing inside each divisor? We are going through all the n elements and we are taking GCD, right? So you would expect that the time complexity is roughly n log n, because the GCD of two numbers takes log of min nm time, right? GCD of two numbers takes log of min nm time. Okay, that's why we get this, and this will be the time complexity. Okay, what about the space complexity? Space complexity. So the space complexity over here, what are we storing? We are first storing the n numbers, and we are also storing the divisors. Everything else is a variable of big O of one space, so we don't need to count that. So basically the total space complexity for this is big O of n plus number of divisors, so that's big O of cube root of n. Okay, this is the space complexity for the problem. Now one additional note, while this is the upper bound, we can have a tighter bound. Okay, additional note. So over here, for the vector of differences, we are just finding the GCD of this entire vector of differences, right? So basically there's a vector and we are finding the GCD of the whole vector. Okay, and there's a fact which I will not prove here, but it's a known fact while doing time complexity analysis. So fact is that GCD of a vector of n elements, so normal GCD, if we use the GCD function in C++, basically Euclid's algorithm for GCD, so GCD of a vector over n elements is actually big O of n plus n log n. Okay, it's big O of, sorry, it's big O of n plus log n not instead of, so this is a tighter bound, right? So that's why it's better than the bound of big O of n log n. The actual time taken is simply big O of n plus log n. And if you want to read more about why this is true, you can see time complexity of GCD over uh, an, an array. All right, so if you go to this, you can get to this Codeforces blog, tighter time complexity for GCD. Okay, it's written by a GM and explains quite well why the time complexity of this list is a very specific big O of n plus log n. Okay, so you can go read that article for why exactly this time complexity analysis is. It is more involved in math, and it really does not matter. Even if it was n log n itself, that solution would still pass. Okay, so now we'll do one final sanity check. Okay, one final sanity check. One final sanity check. Before submitting, you should always, not always, if you have less time, obviously you cannot, but most of the time you should check. We'll put n equals 2 times 10 to the power 5 and see what, see rough approximation, rough approx number of operations. Okay, rough approx number of operations we get using the time complexity formula. Okay, to just ensure that it's within 10 to the power 8 operations, which we can do in 1 second, right? Okay, so let's go to Desmos, because the calculator on Desmos is pretty nice, and we will plug in the equation which we found for time complexity, which is the corrected equation is big of n plus root n plus cube root of n times n plus log n. Okay, so this is the corrected equation for this, right? If you simplify this, or by only keeping the dominant terms, by simplifying this by only keeping the dominant terms, then you can only simply write it as big of n cube root of n. Okay, so if you simplify by removing the non-dominant terms, although for our Desmos calculation we'll keep all the terms. Okay, so let's get into the Desmos calculation. So we need to find n plus square root of n plus n to the power 1 by 3, right? N to the power 1 by 3, which is cube root of n plus log n. Okay, n plus log n. Now we can add n equals 2 times 10 to the power 5, 10 to the power 5. Yeah, and as you can see, this is roughly 10 to the power 6 operations, like 1 into 10 power 6 roughly operations. 10 power 6, 10 power 7, right? So it's between something like that. It is definitely not 10 power 8, right? So it's below number of, well below the number of operations limit. Okay, even if it was n log n, it is still below 10 power 8, so there is no issue. Okay, but yeah, the exact tight bound is n plus log n. Also, you can improve this square root by using a sieve approach to directly find the divisors, right? So this is the final time complexity and space complexity for the problem. And the main logic here, the main logic, let's have a recap. The main logic was to observe that the absolute value of the difference, right, the amount that is changing, that is divisible by m, right? That is divisible by m. So that simply helps us find the maximum value of m, which we can check greater than or equal to 2. And the other observation is that number of divisors is cube root of n. So we can just brute force over all divisors and count our points. Okay, so that is the two observations required here. The topics for this question are mostly number theory and math, right? Topics: number theory, math, brute force, right? So if you found this question difficult, then you should focus more on these topics. All right then, thank you for watching and hope you learned something.